The three-dimensional matching problem. We begin by discussing the three-dimensional matching problem, which can be motivated as a harder version of the bipartite matching problem that we considered earlier. We can view the bipartite matching problem in the following way. We are given two sets X and Y, each of size n, and a set P of pairs drawn from X multiplied by Y. The question is, does there exist a set of n pairs in P so that each element in X union Y is contained in exactly one of these pairs? The relation to bipartite matching is clear. The set P of pairs is simply the agencies of the bipartite graph. Now, bipartite matching is a problem we know how to solve in polynomial time. But things get much more complicated when we move from ordered pairs to ordered triples. Consider the following three-dimensional matching problem. Given disjoint sets X, Y, and Z, each of size n, and given a set T, which is a subset or equals to the product between X, Y, and Z of ordered triples, does there exist a set of n triples in T so that each element of X union Y union Z is contained in exactly one of these triples? Such a set of triples is called a perfect three-dimensional matching. An interesting thing about three-dimensional matching, beyond its relation to bipartite matching, is that it simultaneously forms a special case of both set cover and set packing. We are seeking to cover the ground set X union Y union Z with a collection of disjoint sets. More concretely, three-dimensional matching is a special case of set cover since we seek to cover the ground set U equals to X union Y union Z using at most n sets from a given collection, the triples. Similarly, three-dimensional matching is a special case of set packing, since we are seeking n disjoint subsets of the ground set U equals to X union Y union Z. Proving three-dimensional matching is NP-complete. The arguments above can be turned quite easily into proofs that three-dimensional matching less than equals to P, which means polynomial time reducible to set cover, and that three-dimensional matching is polynomial time reducible to set packing. But this doesn't help us establish the NP-completeness of a three-dimensional matching, since these reductions simply show that three-dimensional matching can be reduced to some very hard problems. What we need to show is the other direction, that a non-NP-complete problem can be reduced to three-dimensional matching. So here's the following. 8.20. Three-dimensional matching is NP-complete. Proof. Not surprisingly, it is easy to prove that three-dimensional matching is in NP. Given a collection of triples T, which is a subset of X times Y times Z, a certificate that there is a solution could be a collection of triples T prime, which is a subset equals to T. In polynomial time, one could verify that each element in X union Y union Z belongs to exactly one of the triples in T prime. For the reduction, we again return all the way to 3 set. This is perhaps a little more curious than in the case of a Hamiltonian cycle, since a three-dimensional matching is so closely related to both set packing and set cover, but in fact, the partitioning requirement is very hard to encode using either of these problems. Thus, consider an arbitrary instance of a 3 set with n variables x1, x2, x3 until xn, and a k closest c1, c2, c3 until ck. We will show how to solve it given the ability to detect perfect three-dimensional matchings. The overall strategy in this direct reduction will be similar at a very high level to the approach we followed in the reduction from three-set to Hamiltonian cycle. We will first design gadgets that encode the independent choices involved in the truth assignment to each variable. We will then add gadgets that encode the constraints imposed by the clauses. In performing this construction, we will initially describe all the elements in the three-dimensional matching instance simply as elements without trying to specify for each one whether it comes from X, Y, or Z. At the end, we will observe that they naturally decompose into these three sets. Here is a basic gadget associated with variable xi. We define elements ai equals to ai1, ai2, and so on until ai2k that constitute the core of the gadget. We define elements bi equals to bi1, bi2, and so on until bi2k at the tips of the gadget. For each j, index j, starting from 1 to 3 until 2k, we define a triple Tij equals to Aij, Aij plus 1, and Bij, where we interpret addition modulo 2k. Three of these gadgets are pictured in figure 8.9. In gadget I, we will call a triple Tij even if j is even, and odd if j is odd. In an analogous way, we will refer to a tip Bij as being either even or odd. These will be the only triples that contain the elements in AI, so we can already say something about how they must be covered in any perfect matching. We must either use all the even triples in gadget I or all the odd triples in gadget I. This will be our basic way of encoding the idea that xi can be set to either 0 or 1. If we selected all the even triples, this will represent setting xi equals to 0, and if we selected all the odd triples, this will represent setting xi equals to 1. Here is another way to view the odd-even decision in terms of the tips of the gadget. If we decide to use the even triples, we cover the even tips of the gadget and leaves the odd tips free. If we decide to use the odd triples, we cover the odd tips of the gadget and leave the even tips free. Thus, our decision of how to set xi can be viewed as follows. Leaving the odd tips free corresponds to 0, while leaving the even tips free corresponds to 1. This will actually be the more useful way to think about things in the remainder of the construction. So far, we can make this even-odd choice independently for each of the n variable gadgets. We now add elements to model the clauses and to constrain the assignments we can choose. As in the proof of 8.17, let's consider the example of a clause. C1 equals to x1 union x2 bar union x3. In the language of three-dimensional matchings, it tells us the matching on the course of the gadgets should leave the even tips of the first gadget free. Or it should leave the odd tips of the second gadget free. Or it should leave the even tips of the third gadget free. So we add a clause gadget that does precisely this. It consists of a set of two core elements, p1 equals to the set little p1 and little p1 prime, and the three triples that contain them. One has the form p1 p1 prime b1j for an even tip b1j. Another includes p1 p1 prime and an odd tip B2J prime. And the third includes P1 P1 prime and an even tip B3J prime prime. These are the only three triples that cover P1, so we know that one of them must be used. This enforces the clause constraint exactly. In general, for clause Cj, we create a gadget with two core elements, Pj equals to the set little pj and little pj prime. And we define three triples containing Pj, capital Pj, as follows. Suppose a clause Cj contains a term t. If a t equals to xi, we define a triple Pj, Pj prime, Bi to j. If the t equals to xi bar, we define a triple Pj, Pj prime, Bi to j minus 1. Note that only clause gadget j makes use of tips Bim with the m equals to 2j or m equals to 2j minus 1. Thus, the clause gadgets will never compete with each other for free tips. We are almost done with the construction, but there's still one problem. Still an open set of clauses has a satisfying assignment. Suppose the set of clauses then we make the corresponding assignment of odd then we even make for the corresponding choices gadget. Of odd this even for at least one free tip for each variable gadget. This leaves at least one free tip for each clause gadget. And so all the core elements of the clause gadget is that we haven't covered all the tips. The procedure, the problem is that we haven't covered 2 nk tips. The triples, the set Tij covered nk of them, and the clause gadget covered an additional k of them. This leaves n-1 times k tips left to be covered. We handle this problem with a very simple trick. We add n-1 times k clean-up gadgets to the construction. Cleanup gadget I consists of two core elements, qi equals to the set little qi and little qi prime. And there is a triple qi, qi prime, b for every tip b in every variable gadget. This is the final piece of the construction. Thus, if the set of clauses has a satisfying assignment, then we make the corresponding choices of odd even for each variable gadget. As before, this leaves at least one free tip for each clause gadget. Using the cleanup gadgets to cover the remaining tips, we see that all core elements in the variable clause and cleanup gadgets have been covered, and all tips have been covered as well. Conversely, suppose there is a perfect three-dimensional matching in the instance we have constructed. Then, as we argued above, in each variable gadget, the matching chooses either all of the even, the set Tij, or all the odd, the set Tij. In the former case, we set xi equals to 0 in the 3-set instance, and in the latter case, we set xi equals to 1. Now consider clause Cj. Has it been satisfied? Because the two core elements in Pj have been covered, at least one of the three variable gadgets corresponding to a term in Cj made the correct odd-even decision, and this induces a variable assignment that satisfies Cj. This concludes the proof, except for one last thing to worry about. Have we really constructed an instance of three-dimensional matching? We have a collection of elements and triples containing certain of them. But can the elements really be partitioned into appropriate sets x, y, and z of equal sizes? Fortunately, the answer is yes. We can define x to be the set of all aij with j even, the set of all pj, and the set of all qi. We can define y to be the set of all aij with j odd, the set of all pj prime, and the set of all qi prime. Finally, we can define z to be the set of all types Bij. It is now easy to check that each triple consists of one element from each of x, y, and z.